Hey everyone, my name is Elal Gilboa. I'm a computer science student at the Hebrew University. Today, I'm excited to walk you through a core component of VeriScan, a cybersecurity image-based threat detection platform designed for digital content authentication. We're diving into copy-move forgery detection. This is a technique used to identify cloned object within a single image. This type of forgery can be used to spread disinformation and propaganda, whether it's duplicating a crowd of protesters to create a false narrative or cloning a patch of grass to hide a sensitive military object. Why is it so hard to detect? Unlike image splicing, where you can bring in content from an outside file, copy-move forgeries use the same image for the source and the target. This means properties like color temperature, noise, and JPEG compression are perfect match. Because traditional methods like error level analysis, ELA, often fail here, we use a key point-based approach. We look for interest points, which are unique textures and edges that are invariant to transformations like rotation and scaling. I'm going to describe my implementation of the algorithm, which is based on an article I will link down below. The implementation follows 4 steps pipeline. First, feature extraction. We convert the image to grayscale and use the shift algorithm to find 128 dimensional descriptors for thousands of key points. Second, matching. We match every descriptor against itself using FLAN, fast library for approximate nearest neighbors. We apply lowest ratio test to ensure we only keep the most distinct matches. Hierarchical clustering. To filter out noise and natural symmetries, we group matches based on their spatial proximity using single linkage clustering. Finally, geometric verification. For each cluster, we use RANSAC to estimate a homography matrix. This confirms if the points moved coherently, suggesting a deliberate clone rather than a random texture. Now I'm going to elaborate on each part of the pipeline, and later I will show you the code implementation and visual examples. Let's talk about SIFT, Scale Invariant Feature Transform. SIFT algorithm provides the raw data for the following steps in the pipeline. This step is critical because it identifies points that stay the same even if the forger rotates the cloned object or resizes it. These geometric transformations are often used in forgeries to make the human eye think the object is different even though it's the same transformed object. This step's output is a set of descriptors. Each key point is turned into 128-dimensional vector. This vector doesn't just store color, it stores the gradient orientation, which is the direction of edges around the point. This is much harder to fake or hide with noise in a forged image. SIFT's output is a hash map of key points mapped to their descriptors. Next comes FLAN, fast library for approximate nearest neighbors. In copy mode detection, every single key point in the image must be compared against every other key point in order to find clones. In a high-resolution image with 5,000 key points, an exhaustive brute force search would require 25 million comparisons. FLAN does this in a much more efficient way by using randomized KD tree. First, it organizes the SIFT descriptors into a tree structure. Instead of checking every point, it only searches branches of the tree that are close to the query point. What does it mean close? We need to use a mathematical threshold, which is called lowest ratio test. FLAN finds the k nearest neighbors for each key point in the tree. Then we calculate the distance ratio between the best matches and the second best match to ensure that the match is distinct and not ambiguous. Let's move forward to hierarchical clustering. Raw matches from FLAN often contain noise, random points that look similar but aren't part of a clone, for example, different leaves in a tree. The logic behind this type of clustering is that the cloned object aren't just single points. They are a group of points that move together to another area in the image. The single linkage method that is used for this clustering process starts with each point in its own cluster and merges the two closest clusters together. To optimize the result, we need to use cut threshold of 25 pixels to differentiate between the clusters. If the distance between two clusters is greater than this, they remain separate. Otherwise, we merge them. This effectively isolates different cloned objects, so they can be verified independently. And last, RANSAC, Random Sample Consensus. RANSAC is the judge that decides if the cluster we've got from the previous step is real forgery or just a natural symmetry. The problem we still have at this step is that even in a forged area, some key point matches will be wrong because they are just too similar, like two identical windows on a building. To solve this problem, we use trial and error approach. RANSAC randomly picks a small subset of matches from the suspected cluster, then calculates a homography matrix that maps the source point to the target points. The next step is testing. It checks how many other points in the same cluster follow that same transformation that the matrix represent. These are called inliners. Finally, a cluster will be determined a clone if there are more than k inliners that move with the same geometric consistency. This number k is dependent on the resolution of the image and the level of details it has. The complicated part of the algorithm is how to find this matrix for each cluster, and I will not dive into that. Okay, so now I'm going to show you some code. This is open source and you can see and use it from my GitHub repository. The link is down below. For implementing this algorithm, you will need OpenCV, NumPy, and SciPy libraries. The main function here is the analyze function. Because this code is part of a greater project, this implementation follows a specific protocols determining the returned values format. So here you can see the constant mean required key points. This is the K I talked about, the number of inliners we will see later on when applying RANSAC. I chose this number because of the recommendations in the article, but you can change it depending on the data set you're using. So here's the steps I described earlier. For the sift part, we will need to convert the image to grayscale, then extract the features. So now we have a list of key points and descriptors. Moving forward, we apply flan on this output to find the k nearest neighbors for each point. This function returns a list of matches. For each point, these are potential clones in the image. We use the lowest ratio. The constant I used is 0.75, and only these results are considered good matches instead of like the entire list we got before. Then we need to verify these results with the following two steps. First, the hierarchical clustering, and then RANSAC. So we do it here in this function, verify geometric consistency. First, we need to create the clusters from the good matches we've got from the flan. Then we use SciPy H cluster module to perform the clustering and apply the 25 pixel threshold to give RANSAC only the results without the noise. Moving forward, now we apply the RANSAC. We can find the matrix using the find homography function from OpenCV. Then we count how many inliners there are in the cluster, following the same geometric consistency. And finally, we determine a clone if the cluster has more than k inliners. That's the constant I talked about before. I chose 4. And then we return the list of clones, and that's it. Okay guys, so this is the final part of the video. I'm going to quickly show you a website which you can download from the database for testing your copy move algorithm with visual examples. So this is the website. Here you can download the dataset. It's a very heavy file. Okay, this is my GitHub repository. You can see everything here, all the files you need, explaining about the entire program. And also you can see here the documentation. I told you about the article before. So now let's move forward to the examples part. So now I'm going to show you a first example of copy move forgeries. So let's start with this example. You can see here an image of weapons. I'm going to show you that the program detects a copy move forgery of one of the guns. So let's see that. So first of all, you can see the entire report. There's an analysis score, description. The program found 119 cloned regions. You can see it here in the analysis results. The key points we talked about earlier are the red dots, and they're connected with a green line to the other cloned area, so you can see the cloned guns here. Let's see another nice image. So let's try this one. You can see the FMO. All these names of images are from the websites I showed you before. F means the fake image, O is the original one, and M is the mask. So let's see this one. You can see here duplicated coins. Okay, so you can clearly see the duplicated part. In this part, he found 276 cloned regions. This number depends on the number of duplicated area and the size of the duplicated area in the image. And that's it. Thank you for listening, and I hope you enjoyed this video. You can like and comment down below.